Hello, welcome to the third module of this last week of our course. Till now in this week we have discussed about a positive feedback motif, we have discussed negative feedback motif, and in this video or in this module I will discuss about a new motif called incoherent feedforward. Let us first look into the structure of this motif. In an incoherent feedforward, you have feedforward. That means from one node two paths starts and those two paths eventually converge to the same node. For example, in this figure you can see the signal is starting from S. S is my input signal. It is converging in two paths and then these two paths again converge at X. So it is a feed forward. The path is diverging from a node and then again converging at a forward node. But it is called incoherent because if you can see from S to X it is a positive path, whereas S to Y to X it is a negative path because Y is inhibiting X. So through one path S is telling X to grow, to get activated or to do something positive, whereas through the other path where you have Y is telling, S is telling through Y to X that you have to inhibit or stop or do something opposite. So two paths are not coherent, they are incoherent. So this is my structure of incoherent feedforward motif. This motif can have different variations, but eventually it will have divergence from one node and again convergence in one node, and two paths will have opposite properties. So we will try to model this network, this motif. So we will simplify this one. This motif can be seen as a combination of multiple Michaelis-Menten processes, but I have simplified this one so that we can understand the basic principles of this motif, basic dynamics of this motif. So what I have considered? I have considered that both X and Y are active molecules. I have not separately shown the inactive state of X and Y. Both X and Y are activated by S, that's what is shown in the figure also, and Y inactivates X. So if this is my basic assumptions, then the model that I have written in terms of ordinary differential equation is like this. The first ODE, dx dt, there is a rate of change of x with respect to time, is equal to k1 into s, that is s is the input signal, and into 1 minus x. This 1 minus x is actually amount of inactive x. So I have active x plus inactive x, the total is equal to 1. So you can consider x as a fraction of total x which is active. The same thing I have considered for y also here. So 1 minus x is actually inactive x. So 1 minus x is inactive x. S is the input signal. S work on inactive x to give rise to active x, that is represented by x. And the last thing in my ODE is k2 into x into y, that is degradation or inactivation. So y is either promoting degradation of active x or y is promoting inactivation of x. So that is my first ODE. The second ODE of my model is for y. So I have dy dt is equal to k3 into s into a term involving 1 minus y. 1 minus y is again the inactive one, inactive y, just like 1 minus x was inactive x. And this whole thing, 1 minus y divided by km, that is a Michaelis-Menten constant, plus 1 minus y, this is coming from my assumption that this activation of y by s is a Michaelis-Menten process. Note that for x, I have not considered any Michaelis-Menten formulation. I could have considered Michaelis-Menten formulation there, but to simplify the model, I have simply considered that x 1 minus x, that is the inactive x, is reacting with S, as simple as that. In this case, I have considered a explicit Michaelis-Menten formulation because I want to study or I want to explain the importance of Km here, the Michaelis-Menten constant here. Otherwise, I could have simply considered just like dx dt. In dx dt, I have considered it is s into 1 minus x. I could have considered here s into 1 minus y or something like that. And the second term in the second ODE is k4 into y. That is, this part is inactivation or degradation of y or degradation of y. So these two are my ODEs, and I want to study the behavior of this motif based on this model, these ODE based models. So let us look into the issues. As we have discussed earlier, I will initially study this system based on nullclines. So let us look into the nullclines. I will first look into the y nullclines. Now before I go into y nullclines, let us make an assumption. Let us consider the system is saturated with total y, that is inactive and active y. So I am considering the amount of y, both inactive and active mixed together, is huge, so that the Km is much less than 1. Remember, 1 is the total amount of y, right? Total y, for me, total y is equal to 1, and that is made up of both inactive and active y. So I am considering the system is completely saturated with y. In other words, that means the Km with respect to total y is very small. So here the total y is equal to 1. That's why Km has to be much smaller than 1. So if this is the situation, and that can happen in many cellular systems, if that is the situation, then I can rewrite the second ODE for y. This is the second ODE for y. What I have considered Km is much smaller than 1. So if Km is much smaller than 1, then I can remove Km from this new denominator. So that's what I have done. I have removed Km from the denominator, and I get this rearranged ordinary differential equation. Note that here I don't have Km. Now obviously, as I have 1 minus y in the denominator and 1 minus y in the numerator, and if they are not 0, I can simply cancel them. So if I cancel them, then I get this ODE. So here dy dt is equal to k3 into s minus k4 into y. So what I have got, look at the first term, k3 into s. That means the production of y depends here only upon the input signal. It does not depend upon how much inactive y is there. This is because the total amount of y is considered so large that my ODE does not depend upon that. It becomes independent of that. It only depends upon the rate of production of y, only depend upon how much signal you give. And that has been achieved because I have considered the system is saturated with y. In other words, I have considered Km is much smaller than the total amount of y, that is equal to 1 here. So that's why in my second ODE at the very beginning I have considered an explicit Michaelis-Menten formulation, so that I can come back and show you that in this case I am considering that the amount of y formed does not depend upon what is the amount of inactive y, because it's a large amount. It primarily depends upon what is the input signal, the strength of the input signal S. So this is my modified ODE. So I will use this modified or rearranged ODE to calculate the nullclines for y. So let us calculate the nullclines for y. To calculate the nullcline for y, I have to consider dy dt equal to 0. So that's what I have considered, dy dt equal to 0. So that means I have to put k3 into s minus k4 into y equal to 0. So I am putting using this ODE here, the modified second ODE here. So now I will rearrange terms so that I get y on one side of equal to sign and rest of the thing on the other side. You don't have x in this equation. So if I rearrange, I get this thing. Y is equal to k3 divided by k4. K3 divided by k4 are ratio of two parameters, so it is a constant, into s. S is my input signal. So you can easily see y is linearly dependent upon s, nothing else, right? So here y is linearly dependent upon s. So let us look into the x nullcline. To get x nullcline, I have to take the first ODE and make dx dt equal to 0. So I will make dx dt equal to 0. So from my first ODE, I get k1 into s into 1 minus x is equal to k2 xy equal to 0. I am getting it from the first ODE that we have written as our model. From first ODE, I am getting this one. Again, I will rearrange x and y. I will put y on one side, x on the other side to get a relation between x and y. So here I rearrange the term. So I get y equal to k1 into s into 1 minus x divided by k2 into x. I separate out the constant term. So I get k1 by k2 as one ratio into s, the input signal, into 1 by x minus 1. This is nothing but this term, 1 minus x by x is nothing but 1 by x minus 1. So I have got this relation here. So this is my x nullcline. And remember here x nullcline also depend upon s. But the relation between y and x is non-linear. So if I have got x nullcline and y nullcline, I can look into the steady state. So I can do that graphically. Before I move into graphically showing x nullcline and y nullcline, let us do some algebra. We know that at steady state both dx dt and dy dt has to be 0. And that is the intersection point of x nullcline and y nullcline. So let us look into algebraically what will be the value of x at this intersection of x and y nullclines. So in other words, I want to know algebraically what will be the steady state value of x. So that calculation I am doing here. So at steady state, dx dt and dy dt both are 0. My nullclines are given here. X nullcline is this one, y equal to k1 by k2 s into 1 minus x minus 1, and y nullcline is y equal to k3 by k4 into s. So I can solve this by equating these two nullcline because I want to find out the x and y value at the intersection of these two nullclines. So I can write 1 by k1 by k2 into s into 1 by x minus 1 is equal to k3 by k4 into s. This is coming from because x and y nullclines are intersecting, so I am putting y value for both of them. So now I can algebraically separate out x. So if I rearranged, I kept this 1 minus x on the left hand side and arranged everything s on the other side. Remember, if s is not equal to 0, then I can cancel this s. So by rearrangement I get 1 by x minus 1 is equal to k3 by k4 into k2 by k1. So 1 by x minus 1 is nothing but a ratio of multiple parameter constants. So if I rearrange the term again, I take 1 on the other side, 1 by x on the other side, and then invert, I get this relation. X is equal to 1 by 1 plus k3 into k2 divided by k4 into k1. Now this is my steady state value of x. This is my steady state of x. Note one interesting thing in this steady state value of x. This steady state value of x does not have y, obviously, and that is obvious because we are separating out y and x, but it also does not have s, the input signal. That means irrespective of the value of s, steady state value of x will remain same. It will only depend upon k3, k2, k4 and k1 which are constant in my system. That means the steady state value of x is insensitive to s as long as s is not equal to 0. That is the condition we have given here, s is not equal to 0. So now look into the whole thing graphically. So this is my x nullcline, this is my y nullcline we have calculated. I have taken some numerical values for k1, k2, k3 and k4 because I have to draw the nullcline plots. And I have considered s equal to 1 to draw these nullclines. So this red line is my x nullcline. This blue one is my y nullcline. You can easily see y nullcline is a straight line or y horizontal straight line and it will vary with s. And y has a hyperbolic relation with x, so it is decreasing with x. And the intersection point here is shown by this yellow dot. And you can easily calculate the value of the intersection point from the previous calculation that we have done. Remember, x is equal to 1 divided by 1 plus k3 into k2 by k4 into k1. So you can put the value of k3, k2, k3, k4 and k1 and it will come that the steady state value of x equal to 0.5. So that's what this dotted line is showing. So here I have steady state value of x at 0.5. Now what will happen if I change s from 1 to 2? That means I am doubling the input signal. What will happen to the steady state? Now from the algebraic calculation I know that the steady state value of x does not depend upon s, it remains constant. So as long as the parameter value k1, k2, k3, k4 does not change, my steady state value of x will not change. Let us see what is happening here. So I change s equal to 2, then my x nullcline is this one, this is my x null, and y nullcline is this blue one. And you can see the gray lines are the older nullclines I have shown in the same plot. Both y nullcline has moved from this gray to this one. X nullcline had moved from this gray line to this one. Both of them has changed because both of them has s, the input signal term in their equation. But their intersection point is this one, this yellow point. And you can easily see at that intersection point, the value of x is 0.5, same that we have got in the previous nullcline intersection. So as I have shown in case of algebraic calculation, here also I am getting that the steady state value of x remain constant at a particular value, and for these numerical values here it is 0.5. That means the steady state value of x does not depend upon what is the input signal. Now if I consider input signal s and steady state value of x as output, then I can say that the output is independent of input signal. I will explain this one further. Before that, let us look into the phase portrait that I have drawn. One can try to draw that manually, but it is rigorous, so I have drawn this using a MATLAB code. Just let us look into the feature of it. The arrows are obviously showing that direction. Now x is in the horizontal axis, y is in the vertical axis. I have drawn the phase portrait considering s equal to 2, and this is my x nullcline, and this is my this yellow one is my y nullcline. Let me erase this one. So now the intersection point is here. So this is my steady state. And you can easily see that is coming at around 0.5. So now if I start near 0, 0, that means at t equal to 0, x is equal to 0, y is also equal to 0, something like that, then my trajectories in my phase portrait is showing that this way I will keep on increasing x, and then I will hit upon here, and then I will follow this path, eventually collapsing here, which is a steady state. You can start from any point, and eventually you can see that you will collapse at this steady state where x equal to 0.5, near 0.5. So in this case, this steady state is actually a nodal sink. So that means this steady state is a stable one. Keep notice on the behavior of x with time. Initially x is increasing, y is not increasing much, and then x start decreasing and collapse at the steady state. So that means if I am starting at 0, 0 for x, y, I have initially a spike of x and then it reaches the steady state. We will get back to this behavior when we will do the numerical simulation using JSIM. So let us look into the JSIM code. I have given the code here. You can copy and try to run it in your own desktop. I will strongly advise you to run it and play around it to understand the behavior of this particular motif. The code is as usual that we have done earlier. Initially you have defined the time. I have kept Tmax equal to 10 here. You have defined two dependent variables, x and y in this case. Remember, my signal, input signal is s, output signal is steady state value of x. And you have defined the parameter values. Note here, I have considered km is equal to 0.001. If you remember in our calculations, the algebraic calculation that we have discussed earlier, we have considered a simplification where we have considered km is much smaller than 1. So to satisfy that, I have kept km equal to 0.001. Then you define the initial values and then the ODEs. So if you compile this code and then run, you will see the behavior of x and y, and that I have shown here. So this is my input signal. Signal of input s equal to 1. So at t equal to 0, both x was at 0 and y was at 0. As I have given the signal, there is a sharp rise in x. X rises sharply with time, then reaches this peak, and then it falls. It falls and reaches a steady state value. So it reaches a steady state here. So initially there is a spike and then it reaches a steady state. Whereas y increases slowly just like a hyperbola and then reaches the steady state. So what is happening here? Actually in this case I have two paths. The signal is going to x from s using two paths, one involving y, one is direct. The path through y is slower. The direct path is obviously faster. So initially there is a sharp rise of x as y path is slower. So that's what I have written here. The path through y is slower than the direct activation of x by s. And that causes a fast rise of x at the initial time points. But then y increases slowly and it catches up the progress of x and then it starts inactivating x. So once it reaches this peak and y reaches here, y become dominant, start becoming dominant, and it tries to inactivate or pull down x, and eventually it reaches a steady state where the effect of s on x for activation and the inactivating effect of y balance each other, and I get a steady state of x. So the steady state of x reaches after an initial spike. Now remember, using algebraic calculation with simplification and the phase portrait, we have shown that the steady state value of x is independent of s. Let us try to see that using numerical simulation using this JSIM code. What I will do here, I will initially keep s equal to 1 and simulate for 10 minutes. So I keep s equal to 1 and simulate for 10 minutes, and this simulation start at t equal to 0 with x equal to 0 and y equal to 0. So after 10 minutes, x reaches a steady state, y reaches a steady state. I note down those steady state values. And then I again do another simulation with s equal to 2. Again simulate for 10 minutes. But in this case, at initial condition t equal to 0, x is equal to x steady state that I have got earlier, and y equal to y steady state. These two values are coming from this simulation, the previous simulation. The steady state values of x and y that I have got in the previous simulation, I use them as initial condition now and increases s to s2. Then what I do? Again I do a simulation with s equal to 3 and simulate it for 10-15 minutes, but here t equal to 0 at initial condition, x is equal to x ss, the steady state value of x that I got from the previous simulation. So that's how I keep on simulating, so that I can show you the effect that how if I switch signal s from 0 to 1, then 2 to 2 to 3, how the steady state behavior of x or the output will change. So I have coupled all these three data sets together to create one single graph here. So you can see initially s, the input signal was 0 basal level. Here at 10th minute I have increased s equal to 1. So s equal to 1 here and kept it for next 10 minutes. So this is my 10 minute. So when I have given this pulse of s equal to 1, I got sudden rise of x up to this spike point, and then it falls and reaches the steady state. Similarly here y increases and reaches a steady state here. Now at this 20 minute I give another pulse of s to make s equal to 2. Now I double s, the input signal is doubled. You can see y increases and stabilizes at a higher steady state value, but x increases with a spike up to this point, and then it falls back and reaches another steady state. Here at this steady state I do the third simulation. I take these two steady state values, this one and this one, as initial condition and give another pulse of s. Now s equal to 3, so s has a higher value here. Here also we consider y this point, this steady state value as initial value and this steady state value of x as initial value. You can see y increases and reaches a higher steady state with time, whereas x increases and then falls back and reaches another steady state value. If I look into these steady states, these three steady states, for s equal to 1, s equal to 2 and s equal to 3, all are actually in the same line, and that is near 0.5. So in this composite graph I can easily see that as I jump s from 1 to 2, 2 to 3, x increases slightly initially, but then it falls back to the same value. It is just like the stabilizer work in your house. If there is a sudden spike in current, there is a sudden spike you get, and then the stabilizer stabilizes the current again to the same value. The same thing is happening here. So in this system, the motif can differentiate between on and off. When s equal to 0, obviously x is also equal to 0, the steady state value is 0. But once you make s non-zero, irrespective of the value of s, whether it 1, 2, 3, 4 or 5, I always get a same higher steady state value of x, which is here close to 0.5. So the system is like this. I have an input which is consecutive and increasing amplitude I am giving. S is changing from 0 to 1 to 2 to 3. And the output, which is nothing but steady state value of x, has a unique behavior that after initial transient spike, x reaches a steady state value which is same for all values of x. In other words, the system is sensitive to on and off state of the input and adapts for all and on values to a same output. That's why this type of motif is called adaptive motif. It can differentiate between on and off state, but for all on state, it reaches to the same steady state, the same output, irrespective of what is the input signal. And this type of behavior, this type of adaptive behavior is very crucial in many cellular processes, where the signal from the outside can fluctuate. But whatever be the signal, as long as it is a on signal, it is above basal level, the system will collapse to the same steady state, the same output. Let us jot down the key points that we have discussed in this module. We have modeled a simple IFF, incoherent feedforward. We can make it complicated, we can consider the complex dynamics of that. To get a understand the basic feature of this system, I have considered a very simple IFF. We have investigated the steady state using nullclines. Then we have shown that when the system is saturated with total Y, or Y nullclines give linear relation with Y and S, then the output of the system, here the steady state value of X, is independent of input, that is S. This is the crucial one. So the output is independent of S, and one key assumption to achieve that, what we have got, is that the system is saturated with Y. In other words, the Km, the Michaelis-Menten constant for activation of Y, was much smaller than total amount of Y, so that I get a relation between linear relation between Y and S. Then the system is adaptive and I get same output for all values of S. We have performed simulation using JSIM, and we have tried to understand the IFF behavior here. And we have shown that the system can discriminate, the motif can discriminate between on-off state of the input. However, for any non-zero input, the output of the system, that is the steady state of X, is same. So the system is adaptive. And one key point here we have to remember, it is not just the IFF, negative feedback in certain cases also can show adaptive behavior. In general, while modeling a cellular process, we have to keep in mind, depending upon the parameter values, both negative feedback and incoherent feedforward can give rise to this type of adaptive behavior. That's all for this module. Thank you for watching.